In this lesson on work, energy and power, we're going to look at power. Starting with the definition, power is the rate at which work is done. It is the change in work with respect to time. If work is done at a variable rate, then it can be defined as power equals the change in work over the change in time. Standard SI unit for power is the watt. 1 watt is the rate of working at 1 joule per second. So that's 1 joule per second. That equals 1 watt, and that's with a capital letter. Variable power. If power is variable, dependent on time, then the work done in an interval is defined as the integral between initial time and final time for our function of time integrated with respect to time. So let's look at some examples. Example 1. A crate of mass 100 kilograms is raised to a height of 18 meters at a constant speed of 0.75 meters a second. Find the power required to do this. So in this example we have a crate of weight 100 g. It's lifted a distance s equals 18 meters at a speed of 0.75 meters a second. So we know that power equals work done over time. So first, if we find the work done is work done against gravity in this case. So I'm going to have the mass, which is 100, times the gravity, which is 9.8, times the height, which is 18. And if we calculate that, we get an answer of 17,640 joules. Okay, the time. This is a simple case of distance equals speed times time, or in this case, time equals distance over speed. So the distance is 18 over the speed, which is 0.75. This gives us an answer of 24 seconds. So therefore, power is going to be 17640 joules, 17,640, divided by 24, which gives us an answer of 735 watts. Okay, so let's have a look at another example. A pump is required to raise 50 kilograms of water a second through a height of 20 meters and discharge it through a nozzle at a speed of 12 meters a second. Find the power required to do this. Well, there's two things going on here. We want to know the work done per second. Everything here is done in terms of seconds. But what we have to do in this case, the power is going to be the potential energy gained per second plus the kinetic energy that's going to be gained per second. Now, by the potential energy, the question said you've got to raise 50 kilograms of water times the gravity, and it's got to be raised a height of 20 meters per second. So if we multiply this together, then the pump is going to have to use 9,800 joules of energy per second just to raise the water. Next, the pump has to give the water a discharge speed, and so that's going to be giving it kinetic energy. Now the kinetic energy is going to be half times the mass, which is 50 kilograms, times the velocity, which is going to be 12, so we're having to give this 50 kilograms of water 12 meters per second velocity. If we multiply these together, we get that we're giving the water a further 3,600 joules of energy. So in that case, the power, and remember that this is work done per second, is going to be the sum of this, so 9,800 plus 3,600, which is 13,400 joules per second. So the power equals 13,400 watts, or we could write this as kilowatts, 13.4 kilowatts. Okay, Let's have a look at one more example. A force is acting on a particle of mass 2 kilograms. It's acting at a rate at 6t squared watts. So sorry, this is just for some reason that hasn't come out on the presentation correctly. So it's come out on a straight line. It says given that the particle initially has a speed of 3 meters a second, find its speed after 2 meters a second. Okay, so what we're going to do in this example is we're going to use the work energy principle. So the work energy principle tells us that we know that the work done equals a change in energy. The reason I'm going to be using the work energy principle is because actually what we're doing is we're going to have that the work done is equal to the final energy. So that's going to be the kinetic energy. Finally, take away the kinetic energy initially. Now I can calculate the work done because we know that the work done, we have if we go back, we have a force acting at a rate of 6t squared. So I can find the work done because the work done, integrating between the initial time, which is 0, and the 2 seconds that it's acting, we're going to integrate that force 6t squared dt with respect to t, so that we get t cubed, 6 divided by 3 is 2, so I get 2t cubed evaluated between 0 and 2. So I get 2 lots of 2 cubed minus 2 lots of 0 cubed. So we get a total of 16 joules. So in this time I know that we've done 16 joules worth of energy. Now I don't know anything about the final energy, but I'm trying to find that final velocity, so we're going to use that final energy to find that final velocity. The initial kinetic energy equals a half m, so we could put that as mu squared because it's initial velocity. The initial velocity has a speed of 3 meters a second. So initially we get a half times the mass, which was 2, times 3 squared, which equals 9 joules. So what I know using my equation from up here, well, let's actually start. If we was to try and find the kinetic energy, the final kinetic energy, I'd have a half mv squared. Let's put the i's on there. So the final kinetic energy is a half times 2 times v squared, which equals v squared. So if I now substitute this into my work energy principle, what I know is that the work done is 16 joules. The final energy is v squared, and the initial energy is 9. So if I add 9 joules to both sides, I get v squared equals 25. And if I square root both sides, remembering that this is going to be just a positive square root because it's going to be a positive velocity, it's increased, we get an answer that the velocity is 5 meters a second. Okay, well I hope that all made sense and that you were able to follow my examples.